You're lying in bed now, the lights are low, and the hum of the world is quieted down. In this soft stillness, I'd like to invite you on a slow and curious journey, a meandering drift through time, thought, and space. Our companion tonight? A mystery as old as starlight itself, the black hole. But don't worry, this won't be a lecture, it's not a test. It's a bedtime story told gently and slowly, just for you, about how the universe hides secrets inside silence, and how darkness can be more comforting than frightening once you understand it. Close your eyes if you haven't already. Let your muscles loosen, your breath slow. There's nowhere to go, no answers to find, just a story to listen to. A quiet, curious story. Let's begin with a thought, not a loud one, just a soft whisper of an idea. What happens when light gets tired? When gravity isn't just a force, but a lullaby pulling even photons down to rest? That's where our story begins. Long before the word black hole ever made its way into our language, long before humanity could even imagine galaxies, we were already watching the sky. You might imagine yourself, in a faraway time, wrapped in rough wool beneath a canvas of stars. No pollution, no noise, just a sky teeming with silent drama. Back then, stars were our calendars, our maps, our gods. But their deaths? Oh, their deaths were unknowable, hidden behind the veil of time and light. Now, imagine falling, not in fear, just the soft sensation of being drawn downward. That's what gravity is. It's not violence, it's invitation, a promise of closeness, and some stars. They fall so far into themselves, they can never return. These are the earliest seeds of the idea. In the late 18th century, an English natural philosopher named John Michell proposed the unthinkable. What if there were stars so massive, so dense, that not even light could escape them? He called them dark stars. You might picture him now, scribbling notes by candlelight. The room smells faintly of oil and ink. Outside, the wind presses against the old windows. He doesn't know what he's glimpsed, only that he has glimpsed something, a shadow in the laws of Newton. Then there was Pierre-Simon Laplace, a Frenchman with a mathematical mind like a clockwork engine. He echoed Michel's thought. Perhaps nature does contain such objects. But few listened. The idea was shelved, too odd, too dark. Centuries passed. The stars kept dying, collapsing. But we didn't know. It wasn't until the 20th century, when Einstein scribbled the equations of general relativity, that the cosmos opened up in a new way. Gravity wasn't a force anymore. It was the bending of space itself. Imagine a bedsheet stretched tight. Now, picture placing a bowling ball in its center. See how it curves? That's how gravity works. Planets and stars curve space, and smaller objects roll toward them. But what if something presses so hard, curves space so deeply, that the well becomes bottomless? That's when the idea of the black hole truly took form, not just as a curiosity, but as a necessity of physics. And yet, the name black hole wouldn't come until 1967 from a physicist named John Wheeler. Before that, they were frozen stars or collapsed stars. There's something poetic about the term, isn't there? Not a hole in the fabric, but a presence. A void so full of gravity that it acts as an absence. You're probably drifting by now, maybe half asleep. That's okay. This story moves slowly, like a photon trying to escape a star that doesn't want to let go. Black holes begin with stars, massive ones, 10, 20, even 30 times the mass of our sun. They burn through their fuel quickly, recklessly, then they collapse inward, not with a bang, but with an implosion, like an exhale that never ends. And the result is a singularity, a point of infinite density. We don't really know what it is. Our math breaks there. It's like dividing by zero, a question the universe doesn't want to answer. Around that singularity forms the event horizon. It's not a surface, it's a boundary, a line you cross and can never return from. Like falling asleep and forgetting the moment you drifted off. You might be wondering, if nothing can escape, how do we know they're real? We know because of what they touch, because they bend light, they steal from nearby stars, they emit X-rays as matter spirals in. They leave footprints, like a creature you can't see, but whose presence bends the forest around it. The first real evidence came in the 1960s and 70s. Cygnus X1, a bright X-ray source in the sky, turned out to be a star orbiting something invisible, something heavy, too heavy to be a neutron star. It was, almost certainly, a black hole. Since then, we've found many more, some solitary, some at the hearts of galaxies, monsters millions or billions of times more massive than our sun. Quiet giants. They don't suck everything in, they don't hunt, they just wait. And when something does come too close, it doesn't fall all at once. It spirals, it dances, it heats up, it screams in X-rays, sometimes for years, before finally vanishing. You might think of it like a whirlpool, calm on the edges, but at the center, a stillness so complete it becomes unknowable. So, tonight, as you drift deeper into stillness, let your thoughts spiral gently, not to be lost, but to come close. Close to the event horizon of understanding, where thought slows, where time bends. We're only just beginning. The black hole is not the end. It's the doorway. Let's imagine, just for a while, that you are a beam of light, not a metaphorical one, not a symbol of hope or clarity, just a particle, a wave, moving through space at the universe's ultimate speed limit. You've never felt the passage of time, not really? Time slows to a crawl when you move like this, faster than anything with mass ever could. You slip past planets and moons, past quiet fields of dust, past the flicker of stars. You're not alone. Photons are everywhere, but you are free. You were born in a star's fusion heart, perhaps, or the final glow of a dying nova. And now you travel. But ahead, there is something strange. Not a wall, not a thing, but a place where the map folds. The gravity isn't just stronger, it's different, warped. It curves space so sharply that all lines bend toward it. You don't slow down. You can't. But you change direction. Not because you want to, but because space itself tilts. This place, this boundary, it's invisible. But it's there, the event horizon. As you cross it, there is no pain, no flash, no change in the way you move. But something essential has shifted. From here, there is no return. Not because you are trapped by a force, but because all roads now lead inward. Outward is no longer a direction that exists. This is what the inside of a black hole is like. Not a prison, not a death. A silence, a stillness. And from outside, your path seems to stop. You appear frozen just above the horizon, forever falling, but never fallen. This illusion, this boundary of time, is part of the mystery. Outside observers, watching you fall, would never see you vanish. They'd see you stretch and fade, slowed by time, red-shifted into oblivion. Light itself changes here. It weakens. It loses color. It becomes memory. But from your own point of view, you fall, freely, quickly, toward the singularity. We can't know what you'd find at the center. The laws we trust begin to unravel here. It's not that they stop working, it's that they speak a language we haven't yet learned. Equations loop back on themselves. Predictions break down. Time and space change roles. Some say the singularity is infinitely small. Others wonder if it's not a place at all, but a moment, a place where past and future kiss. It's quiet inside a black hole, not just in sound, but in meaning. There are no landmarks, no borders, no clocks, just inwardness. The universe curling inward upon itself. Back outside, a star is watching, or maybe a planet. Or maybe you, lying quietly beneath your blanket, listening. You're very far from that place, but still, it affects you. Gravity has no limit to its reach. A black hole, a billion light years away, still pulls gently on your atoms, like the softest thread tugging from across the cosmos. The Earth, in its slow orbit, wobbles, and instruments, tiny, precise, pick up echoes of collisions, ripples in space-time, gravitational waves. They were first confirmed in 2015, after two black holes spiraled into each other, billions of years ago. The collision sent a shudder through reality itself. That ripple passed through you too. It passed through your room, your thoughts. It stretched and compressed space itself by less than the width of a proton. But it was real. The detectors, twin beams of light bounced between mirrors, sensed it. And for a moment, we knew. Two black holes had met. They had merged. And the universe had sighed. This is how we know they are real. Not through pictures, not through sight, but through listening. The cosmos is full of quiet music if you know how to hear it. Now imagine being on the edge of one. There is something called the photon sphere, a place just outside the event horizon where light itself can orbit, not fall in, not escape, just circle forever. It's a strange kind of trap, a perfect delicate balance, light running laps around a darkness it cannot flee. You might think of it as a dream that loops, a thought that never resolves, a memory circling your mind. Further out still is the accretion disk, not part of the black hole, but shaped by it. Gas and dust swirl, heating to immense temperatures. Matter screams as it falls in, louder than anything in the universe. But we hear it not in sound, but in X-rays, in jets, in patterns. From a great enough distance, you might see the disk shine brighter than a galaxy. The black hole itself is invisible, but its appetite is not. And that contrast, it tells a story. When matter falls inward, it doesn't simply vanish. It resists, it fights, it radiates. And in that struggle, it becomes visible. All of this. From an object that does not emit light. From a presence so complete, it becomes absence. And yet, there's more. In the 1970s, a physicist named Stephen Hawking proposed something strange. He imagined quantum particles flickering into existence at the edge of the event horizon. Normally, these pairs of particles would annihilate each other instantly. But if one falls in, and the other escapes, then energy leaves the black hole. Over vast timescales, it could evaporate, slowly, gently, like mist in morning light. We call it Hawking radiation. We've never observed it directly, but the idea is beautiful. It suggests that nothing is truly lost, that even the blackest hole whispers over time until it fades. Imagine that. A black hole born from the collapse of a massive star, feeding, merging, growing for billions of years. Then, at the edge of eternity, losing mass, radiating softly, and one day, far beyond human memory, it vanishes, leaving behind no sound, no light, just a faint tremble in the fabric of what once was. That's the kind of story the universe tells. Slow, gentle, patient. Not every black hole is the same. Some are small, stellar remnants just a few kilometers wide. Some are giants, supermassive hearts of galaxies, millions of times the mass of our sun. And some may be even stranger. Primordial black holes. Born not from stars, but from the early universe itself. Tiny, chaotic pockets of energy collapsed into themselves before atoms ever formed. They might still be out there, drifting, hiding. It's hard to say what's real and what's imagined when it comes to black holes. But isn't that the case with dreams too? You don't need to understand every piece. Just let the thoughts pass by, like clouds. You're not solving anything tonight. You're resting. Your mind may circle back, the way light orbits near a black hole. It may return to the same idea, the same wonder. That's okay. The story will hold it, like gravity, like memory. There's still so much more to see, so much that hasn't yet been told. But there's time. Let your breath slow. Let your muscles soften again. The universe is dark, yes, but it is also calm, spacious, full of invisible kindness. You are not falling, you are floating, and the stars are still watching. There is a black hole at the center of our galaxy. It sits in the heart of the Milky Way, quiet and massive, surrounded by the slow, looping orbits of stars that should not be able to move the way they do. They arc and swing around something invisible, something that emits no light. Their paths trace an unseen presence, Sagittarius, a star 4 million times the mass of the sun, packed into a space smaller than our solar system. For decades, astronomers watched those stars, patiently, carefully. They tracked each flicker of motion, each curve and change. The orbits were not random. They followed rules. But the rules only made sense if something vast and hidden were there, anchoring the galaxy in place. It doesn't dominate the sky. It doesn't pull everything in. It waits. In the galactic core, surrounded by gas, dust, and countless stars, it holds the Milky Way in quiet balance. Black holes like this are found in most galaxies we observe, not at the edges, but at the center, as if galaxies themselves form around them, spiraling out like leaves around a still pool. The origin of these supermassive black holes is still unclear. They may begin as smaller black holes that grow by feeding, or they may have formed in the earliest ages of the universe, seeded by chaotic, dense knots of matter, collapsing before the first galaxies even cooled. In some distant systems, we see signs of dual black holes, pairs caught in slow orbit around one another, remnants of galactic collisions. When galaxies merge, their stars rarely crash, but their black holes spiral together over eons, drawing closer and closer, warping the fabric of space with each pass until they finally become one. These mergers send out gravitational waves strong enough to be felt across the universe. They ripple outward, distorting time and space as they go. Not just explosions, but rearrangements of reality. Each wave is a message, a record of an event that happened before humans walked the earth. We detect it long after the fact, like hearing thunder hours after a storm has passed. The deeper we look, the more we realize that black holes are not exceptions. They are part of the structure. They influence the way galaxies form, the way stars are born, the flow of gas and light. They are not rare. They are not exotic. They are woven into the shape of things. Some black holes move. In the vast dark between galaxies, there may be black holes ejected by cosmic collisions, cast out of their homes by slingshot gravitational interactions. Alone, silent, invisible, drifting through the void. They carry with them the memory of chaos, the aftermath of galaxies merging or dying, the silent consequences of cosmic violence. Without a disk of gas or stars to reveal them, they are impossible to see. But they're there, moving, not toward anything, but simply onward. And yet, not all black holes are so vast. Some are small, remnants of stars no more massive than a few suns. They are born when a supernova collapses inward and leaves behind a dense core. These stellar mass black holes are harder to find. They do not glow. They do not shine. They hide unless they feed. In binary star systems, a black hole can siphon matter from its companion. The gas spirals inward, heats up, emits X-rays. These systems flare and pulse, revealing themselves briefly before fading again. Over time, such black holes may consume their neighbors, not in an instant, but slowly, drawing matter bit by bit, reshaping the orbit, changing the balance. But there's another path too. Some stars do not explode. They collapse directly, silently, folding inwards without a sound. No flash, no shockwave, just disappearance. One moment, a star. The next, a shadow. This quiet formation leaves no supernova remnant, no fireworks. It simply ends. Black holes may also be born from neutron stars, some of the densest objects in the universe, if they gain too much mass. A neutron star is already compact, a sphere of degenerate matter packed so tightly that a teaspoon of it would weigh more than a mountain. But even that pressure has limits. Feed it more mass, and it cannot hold. It collapses further, and in that final surrender, it becomes a black hole. Not every black hole remains quiet. Some flare, some erupt. Active galactic nuclei, or AGNS, are powered by supermassive black holes that are feeding, pulling in gas, dust, and stars at an astonishing rate. As the material falls inward, it compresses and heats, emitting tremendous energy. From these feeding frenzies come quasars, some of the brightest objects in the universe, visible from across cosmic time. Their light crosses billions of years to reach us, carrying a record of the early universe. And yet, at the heart of every quasar is still a void, a silence, a black hole. Some launch jets, beams of plasma that extend for hundreds of thousands of light years, powered not by what goes in, but by what is turned away. The magnetic fields twist and sling particles outward, perpendicular to the accretion disk at near light speeds. These jets pierce through galactic halos, carving paths into intergalactic space, shaping entire clusters of galaxies. It's a paradox. The thing that lets nothing escape gives rise to the most spectacular displays. Not from within, but from the edge. The event horizon defines what is lost. But just outside that line, chaos and light dance in the most energetic forms known to science. And still, it's the quiet that draws us. The idea that beyond that boundary lies a place where space ends, where time curves inward, where causality frays. Some theories suggest that inside a black hole, space may not just end, it may reconnect. That black holes might contain bridges, tunnels through space and time, wormholes. There is no evidence for this, no observation, only math teasing out the possibilities. Some equations allow for a connection between a black hole and a white hole, a hypothetical object that cannot be entered from the outside, but from which matter might emerge. No white holes have been found, but the math whispers. And in those whispers, we hear echoes of stories told in the quiet of theoretical physics labs. Chalk on blackboards, papers passed back and forth, minds trying to peer past the event horizon using symbols and conjecture. One puzzle lingers. What happens to information? When something falls into a black hole, matter, light, atoms, particles, it carries information. The patterns of its structure, the arrangement of its quantum state. If a black hole evaporates, as Hawking proposed, where does that information go? If it is lost, then the fundamental laws of physics, laws that require information to be conserved, are broken. If it remains, how is it stored? This is the black hole information paradox. It sits at the center of theoretical physics, unsolved. It points towards something incomplete in our understanding. Some believe information is stored at the event horizon itself, encoded like a hologram. Others argue it leaks out through subtle patterns in Hawking radiation. There are models, proposals, debates, but no answers yet. It is strange that the most perfect solution in general relativity, a black hole, reveals the gaps in our knowledge. It is as if the universe constructed a mirror, and in looking too closely, we find our reflection incomplete. The study of black holes has reshaped cosmology. They are not just curiosities, they are laboratories for physics, for time, for information. They teach us by their silence. They answer questions with questions, and still they remain. Not at the edge of the universe, but in the heart of it. Not distant, but near, interwoven. Black holes are not empty. They are full of memory, of history, of unanswered questions, and they wait. They wait not because they are conscious, not because they choose to, but because waiting is simply what they do. The universe changes, galaxies collide, stars are born and die, and through it all, black holes remain. Their lifespans stretch longer than anything else we know. Trillions of years, quadrillions, longer than the age of atoms, longer than the reign of light. In a far future, when the stars themselves are gone, burned out, collapsed, or cold, black holes will still be there. The last luminous traces will be gone, and the cosmos will be dark. A black-on-black silence. This era is called the black hole era, and it lies at the end of the universe's timeline, far beyond what we can truly imagine. All that will remain are black holes, drifting slowly through a frozen sea of subatomic particles and cold, empty space. They will not last forever. Even the largest black holes will slowly, inevitably evaporate. Through Hawking radiation, through quantum fluctuations, they will lose energy particle by particle, photon by photon. The process is almost unimaginably slow. A black hole with the mass of our sun would take 1,067 years to vanish. The universe is only 13.8 billion years old. We haven't even begun to see the first flickers of that long goodbye. And when they do evaporate, at the very end, there is no explosion, no grand finale, just a sigh of fading heat, a whisper of thermal energy, and then nothing. A black hole dies not with a bang, but with a dimming that slips beneath notice. What remains? No one knows. Do the black holes leave behind echoes? Does information seep back out in some disguised form? Or is it gone, rewritten into the vacuum itself? Some physicists believe the final burst, the last moment of radiation, may carry with it the essence of all that fell in, compressed, scrambled, but there. Others think it's lost forever, woven into the fabric of space-time in ways we cannot retrieve. If black holes are puzzles, they are also records, cosmic ledgers of everything that ever fell too close, stayed too long, gave up too much momentum to resist the fall, and so every black hole is a biography, not of one thing, but of many, of gas clouds and stars and planets, of photons and gravity waves, all inscribed in a language we have not yet learned to read. In the early universe, conditions were different, denser, hotter, chaotic. That's where the idea of primordial black holes comes in. Objects formed not from stars, but from energy itself. Collapsed regions of space-time birthed by fluctuations during the first second after the Big Bang. These black holes could be tiny, smaller than an atom, but incredibly dense. Or they could be massive, seeded before galaxies even existed. If they formed, some may still be out there, hiding in the dark, invisible unless they collide with something we can see. Some have wondered if dark matter, this elusive invisible mass that makes up most of the universe's structure, might be composed, at least in part, of these primordial black holes. Not particles, but ancient absences. Mass without light. The search continues. We map the sky. We study the bending of starlight, the patterns in galaxies, the shadows cast by nothing. We search for flickers and distortions that hint at something unseen. And sometimes we find more than we expect. In 2019, a picture was released. It was not a picture in the usual sense, not light reflected from a surface, but an image stitched together from the shadows and radio waves gathered by telescopes across the globe. A collaboration called the Event Horizon Telescope had captured the silhouette of a black hole at the center of galaxy M87. What we saw was a ring of fire, a glowing halo of gas, bright with energy, circling a darkness that did not shine, a circular void, framed by the light of matter just before it fell in. It was the first time we had seen the shadow of the event horizon, the outline of a place from which no information escapes. The image is not sharp, not detailed, but it is unmistakable. It confirmed that black holes are not just ideas. They are places, real structures with real effects. The shadow of M87's black hole was exactly the size predicted by Einstein's equations. 100 years of theory, proven by a ring of light bending around a hole in space-time. Other images have followed. Sagittarius. A star, the black hole in the heart of our own galaxy, was captured too. More difficult to see, more chaotic, but there. As the data improves, the shadows grow sharper, the outlines clearer. The unknown becomes less distant, less abstract. But the mystery remains. Each observation deepens the question, what is a black hole, truly? Not just what it's made of, but what it means. Black holes challenge our ideas of space, of time, of cause and effect. They turn the arrow of time inward. They suggest that information might be stored on surfaces, not volumes. That the boundary of a thing may hold more truth than its center. This is the holographic principle, an idea from string theory that the entire contents of a region of space can be described by data encoded on its boundary. Applied to black holes, it means the information of everything that falls in might not vanish at the singularity, but be stored on the event horizon, a two-dimensional surface encoding a three-dimensional truth. It's not proven, but it's elegant. And it points to a deeper strangeness. If black holes store information on their boundaries, then maybe the entire universe is like that. Maybe reality itself is a projection, a three-dimensional experience cast from two-dimensional rules at the edge of the cosmos. We don't know, but it is black holes that lead us to such thoughts, not because they reveal, but because they hide. They mark the place where our knowledge runs out. In science, such boundaries are not endings. They are invitations. An invitation to look closer, to think differently, to imagine further. Each question that cannot be answered by the standard model, each mystery that general relativity cannot resolve, points back toward the black hole, not as a failure, but as a teacher. Not everything lost is gone. Not everything hidden is unreachable. The night sky is full of silent markers, places where light ends, places where time becomes geometry, and geometry becomes fate. The universe is not empty. Even in its darkest places, it is full of meaning. And so, we continue to trace the edge of the unknown. In tracing the edge of the unknown, we find ourselves returning again and again to the question of where black holes begin, not only in space, but in time. The earliest stars, the first to ignite in a cooling universe, were massive beyond modern comparison. These primordial giants, known as population 3 stars, formed from clouds of pure hydrogen and helium, untouched by the metals and elements created in later stellar generations. With no heavier atoms to cool their fiery cores, they grew enormous and lived brief, brilliant lives. And when they died, they did not fade. They collapsed. Some may have exploded into supernovae, seeding the cosmos with carbon, iron, oxygen, the ingredients of future stars, of planets, of life. But others likely collapsed directly into black holes, vast and ancient, born before galaxies had spiraled into shape. These early black holes might have been the seeds of the supermassive ones we observe now, their growth fed by the collisions of stars and the gathering of primordial gas. They would have grown quietly at first, hidden behind veils of dust, invisible but patient. Over time, they drew in more matter, became centers of gravity around which the first galaxies assembled. And still, they remain. The black holes we study today are not young. They are survivors of cosmic evolution. Their existence tells the story of matter and time, of collapse and assembly. They hold within them not only mass, but history. In observing them, we are looking backward, peering through layers of space and time. The light that reaches us now from distant quasars, from ancient X-ray flares, has traveled billions of years to arrive. We are not just seeing objects, we are witnessing ancient events unfold. Even now, new black holes are being born. When massive stars exhaust their fuel and can no longer support themselves against gravity, they collapse inward. The process is violent, but the end is quiet. What remains is invisible. There are stars in our own galaxy nearing that fate. Blue giants burning fast and hot. Red supergiants slowly pulsing their last layers of hydrogen into space. When their time comes, they will collapse. Some will leave behind neutron stars. Others will go farther, forming black holes that will orbit silently through the Milky Way for billions of years. Some may already have. There may be millions of black holes in our galaxy alone. Most are dark, unaccompanied, and silent. Without a nearby companion to feed them gas, they are invisible to us. But they are there, exerting their gentle pull, warping the paths of stars, drifting in long ellipses through the galactic disk and halo. We find them only when they interact, when they cause a star to wobble in an unexpected way, when they produce a microlensing event, briefly magnifying the light of a distant star as they pass in front of it. These events are rare, but unmistakable. Even in silence, black holes make their presence known. There is a kind of elegance to their simplicity. A black hole is defined by only 3 measurable properties: mass, charge, and spin. Everything else, composition, structure, origin, is lost behind the event horizon. This idea is captured in the no-hair theorem. Black holes have no hair, no distinguishing features beyond these 3 qualities. 2 black holes with the same mass, spin, and charge are indistinguishable, regardless of how they formed. And yet, behind that sameness, each one holds a different story. 2 black holes of identical mass may have been born in different epochs, from different stars, in different corners of the universe. One might be the child of a collapsed giant, the other a remnant of a galactic core, but once formed, they become indistinguishable. It's a reminder of how the universe smooths away detail with time. In the long run, complexity fades, temperature equalizes, stars burn out, particles decay. And in the end, only a few structures remain: photons, neutrinos, and black holes. And beyond that, perhaps only the void. But not all ideas about black holes are settled. In recent years, the black hole firewall paradox has stirred debate. According to classical general relativity, crossing the event horizon should be uneventful, no physical barrier, no sudden force, just a smooth passage into a deeper gravitational well. But some theories suggest otherwise. If information is preserved, as quantum mechanics requires, then something strange must happen at the horizon. Some physicists have proposed that the event horizon might become a firewall, a region of high-energy particles that would destroy anything attempting to pass through. Others reject this. They argue that the smooth geometry of general relativity must hold, that the paradox points to a deeper, as yet undiscovered principle of quantum gravity. No consensus has been reached. The debate touches on the deepest questions of physics, about how reality is stitched together, about whether space and time are continuous or made of discrete quanta, about whether space-time itself is an emergent phenomenon, rising out of deeper, more fundamental rules. Black holes sit at the heart of this mystery. They are where our best theories meet and fail to reconcile. And that failure is productive. It pushes science forward. Each paradox is a signpost, pointing to something missing, some overlooked piece of the puzzle. Some physicists believe that resolving these paradoxes may lead to a theory of everything, a single framework that unifies gravity with quantum mechanics. Others are more cautious. The answers may be more subtle, more strange. Still, the questions persist. In the meantime, we observe, we measure, we build more sensitive instruments, launch more precise telescopes, gather more data from the edges of black holes and the ripples of their collisions. We test predictions, we refine equations, we compare maps to reality. And slowly, the picture becomes clearer, not simple, but clearer. Black holes are no longer the stuff of science fiction. They are part of the scientific canon. We've seen their shadows, felt their gravity, heard their mergers. We know they spin, that they can launch jets, that they can grow, that they can evaporate. We know that the universe is full of them. But the knowing is not complete. There is still something just out of reach, something just beyond the horizon. A question not of physics, but of interpretation, of meaning. Why does the universe permit such places? Why does it allow for singularities, points of infinite density where the laws of physics break down? Why is information preserved? Why do the deepest questions of space-time lead again and again to the event horizon? We do not know. But the questions remain, and in them, we find purpose. In the space between stars, where light travels for years without meeting a single atom, time unfolds differently. Not faster, not slower, but wider, more indifferent. In that deep silence, black holes continue their quiet influence, shaping the future even as they carry the past. Some of the black holes that exist now were formed long before Earth cooled, before the first single-celled life forms began drifting in ancient oceans. They have outlived the empires of stars. They have seen the light of galaxies bend and redden with age, and in a future still waiting to be born, they will remain. The eventual fate of matter is often imagined in decay. Protons may disintegrate, neutrons may dissolve, even atoms themselves may fall apart. If this is true, if the building blocks of matter are not forever, then black holes become the custodians of what once was. They will persist through the era of star death, through the evaporation of white dwarfs and the cooling of neutron stars. The galaxy will dim, the night will deepen, and only the long, slow draw of gravity will continue to move what little mass remains. Black holes will consume what drifts near them, not as predators, but as the final resting place of mass and momentum. They are the furnaces of the end, burning without flame, heating space not with light, but with curvature. One by one, in a process measured across trillions of years, they will evaporate. Larger ones live longer. Supermassive black holes will be the last to go. For a time, they will rule a dark and empty universe, their presence known only by the whisper of quantum evaporation at their edges. Eventually, even they will vanish. And with that, the last complex objects in the universe will be gone. What remains then? A faint bath of radiation, evenly spread, near absolute zero. A universe no longer structured by galaxies or stars, but by probability and temperature. The timeline stretches further than human imagination can comfortably reach. This isn't just the end of stars, it's the end of narrative. Entropy will rule, not through chaos, but through silence, through uniformity. The structures we understand, atoms, molecules, light, will fade into a sameness so complete it can no longer be described in terms of events. And yet, even here, the legacy of black holes remains, not only in the energy they release in their final stages, but in the questions they leave behind. Questions encoded in the physics of collapse, of information, of dimensionality. What if black holes are not only endpoints, but seeds? Some speculative theories imagine that When a black hole forms, it does not simply collapse to a singularity, but punches through the fabric of our universe. On the other side, a new universe, a bubble of space-time branching off from our own, expanding in its own dimension, disconnected yet birthed from the gravitational collapse in ours. Each black hole, in this vision, becomes the Big Bang of another universe. It's not a theory we can test, not yet, but the mathematics allows for it, and the consequences are profound. If true, it means the act of collapse is not just a death, but a kind of reproduction. One universe begets another, a cosmic tree, each black hole a seed pod, each singularity a germination. In this way, black holes may be not only the graveyards of stars, but the wombs of worlds. It leads to a concept called cosmological natural selection. If universes are born from black holes, and if the laws of physics in those offspring universes can vary slightly, then perhaps the universes most likely to produce black holes are the ones that leave the most descendants. In this view, the very laws of our universe may be tuned, not for life, but for black holes. Stars that live long enough to form complex matter, gravity strong enough to collapse mass into singularities, a cosmos that rewards formation, not for survival, but for replication through collapse. It's a theory that shifts the perspective, not human-centric, not even life-centric, but structure-centric, pattern-centric, a universe optimized not for thought, but for curvature. And if it's true, it means our universe may be one of many, part of a lineage not recorded in time, but in the silent births and deaths of singularities. But none of this explains the most basic mystery. What happens at the singularity? All our equations fail there, not just become inaccurate, but break down entirely. It is a point where our physics ends. The curvature becomes infinite. Density becomes undefined. Time itself stops making sense. Not because it literally ends, but because our tools, our symbols, our numbers cannot describe it. Some physicists believe that singularities don't exist at all. They argue that what we call a singularity is simply a symptom of incomplete theory, that in a future quantum theory of gravity, the singularity will be smoothed away, replaced by some new description, something finite, understandable. Perhaps space-time is made of loops, or strings, or something else entirely. Tiny, vibrating structures that give rise to mass, force, and dimension. In these theories, the singularity is replaced by a region of high curvature but finite volume, a place where the known laws still function, but in different ways. We do not yet know what this structure is, but we are searching. Experiments at particle colliders, observations of neutron star collisions, studies of cosmic microwave background patterns, all are looking for traces, for hints. Even the data from gravitational wave observatories may one day show us differences between real black holes and the idealized ones described by relativity. A deviation, a crack, a signature. Something that says, here, the new physics begins. It is no longer just about looking inward. It is about listening for the faint difference in timing, the barely perceptible tremor in the ring down of a merger, the missing echo in the silence. These are the signs we search for, not because they answer everything, but because they point toward the next question, and the next. This is what black holes teach us. Not only how to understand mass and light, but how to follow a question into the dark. To keep asking, even when there is no reply. To find meaning not in the answer, but in the asking. The asking continues, and in doing so, becomes its own form of exploration. An expedition not across terrain, but across the boundaries of knowledge itself. Black holes mark the borderlands, the place where everything we know reaches its limit, and everything beyond becomes possible. To understand them better, we began simulating them, not just with equations on paper, but with entire virtual universes constructed from raw computation. Supercomputers now model what happens when two black holes spiral into each other, not as still objects, but as spinning, wobbling vortices of curved space-time. These simulations help us see what cannot be seen, to predict the shapes of gravitational waves, the flickers of light that might emerge from the surrounding gas. They help us test general relativity with precision, not abstractly, but dynamically, in real, shifting curved space. The predictions match the data. With each new merger detected by LIGO and Virgo, The fingerprints of Einstein's equations are confirmed. Again and again, the universe behaves as it should. And yet, the precision of our theories only sharpens the mystery. Because even though relativity works perfectly in these vast, elegant simulations, it still breaks inside, at the singularity, at the edge of understanding. And so, we model the outside: accretion disks, relativistic jets, warped orbits, but the inside remains unreachable. Not through stubbornness, but through definition. The event horizon is not just a boundary of escape, it is a boundary of knowledge. No signal can cross it outward, no light, no gravity wave, no piece of information. And so, the interior becomes not just a place we cannot reach, but a place we cannot even describe. Still, we try. Some theories suggest that space inside the event horizon becomes time, and time becomes space. That direction collapses inward, and what once was a location becomes a moment. You do not fall through space, you fall through time. Others propose that space continues inside, in a warped and compressed form, that the singularity is not a point, but a twisted dynamic core, perhaps ring-shaped in the case of rotating black holes. And some propose that there may be no inside in the way we think of it at all, that the black hole is a boundary condition, a surface effect, and that our desire to visualize an interior is a projection, a misunderstanding rooted in our everyday experience of dimensions. Then there are the extremal black holes, mathematical curiosities with maximum spin or charge. Perfectly balanced, they sit at the edge of physical possibility. Their event horizons behave differently. Their thermodynamic properties shift. They are not known to exist in nature, but they help us understand the edges of our theories. There are analogs, too, ways of mimicking black holes in the lab. Physicists have created acoustic black holes in Bose-Einstein condensates, where sound waves cannot escape from a central region. Others have created optical analogs using light in nonlinear media. These are not true black holes, but they echo the mathematics. They show us how the concepts may be universal, emerging not from mass alone, but from the structure of fields and flow. They point to something deeper, that black holes may not just be things in space, but patterns in physics. That what defines them is not their substance, but their relationships. The way they bend, the way they prohibit return, the way they encode what they consume. And in that encoding lies one of the deepest questions of all: entropy. Black holes, according to the laws of thermodynamics, must have entropy, a measure of information, of hidden microstates. But entropy in physical systems usually arises from complexity. A gas has high entropy because there are many ways its molecules can be arranged while appearing the same at the large scale. A black hole, by contrast, has only mass, spin, and charge, no visible complexity. And yet, its entropy is enormous. The entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This strange fact led to a revolution in theoretical physics. It suggests that the information content of a region of space may be encoded on its boundary. This is the foundation of the holographic principle, the idea that everything within a volume of space can be described by data on its surface. It is not just a poetic image. In string theory, in particular through the SCFT correspondence, this principle becomes precise. A theory of gravity in a bulk space is equivalent to a quantum field theory on its lower dimensional boundary. This duality between gravity and information, between space and boundary, has become one of the most fertile grounds in modern physics. And it all began with black holes. They are the testing grounds for these ideas, the crucibles in which our understanding of quantum theory and space-time are forced to coexist. The strange link between geometry and information has led some to suggest that space-time itself is emergent, that it arises from the entanglement of quantum bits, that the fabric of reality is woven not from position and velocity, but from relationship and correlation. This would mean that black holes are not just mysterious, they are foundational. They are not exceptions to the rules of the universe. They are the purest expression of them, the cleanest geometry, the most extreme thermodynamics, the deepest symmetry. And as we try to describe them, we find ourselves speaking not in images but in principles: causality, unitarity, symmetry, entropy. These are not the properties of things. They are the rules of existence itself. And black holes sit at the point where all those rules meet. They are the fulcrum between energy and space, between time and temperature, between observation and abstraction. That they exist in the real universe, observable, measurable, photographable, is astonishing. It is as if the most abstract structures in mathematics walked into the world and took form as shadows in the sky. We name them as if we understand them: black hole, event horizon, singularity. But these are not answers. They are placeholders. They are markers of our ignorance, draped in language. And so we continue, observing, measuring, modeling, wondering, not to defeat the unknown, but to be near it, to feel its presence in the equations, in the data, in the silence between stars. Silence in the presence of black holes is not an absence but a weight, a thick, curved stillness, the silence of a place where cause does not guarantee effect, where motion continues but meaning stutters. It is here, at the confluence of space, time, and entropy, that we begin to lose our grip on the familiar. Still, we build our understanding layer by layer. In the 1970s, Jacob Bekenstein first proposed that black holes must carry entropy, that something was missing in our accounting of thermodynamic laws if black holes could swallow information and reduce entropy outside, without any corresponding internal change. Stephen Hawking resisted the idea at first, until his own calculations, using quantum field theory in curved space-time, showed that black holes emit radiation. It was an extraordinary conclusion. Black holes aren't entirely black. They glow, very faintly, very coldly, but with unmistakable consequences. This Hawking radiation is not emitted from within the black hole. It arises at the edge, the event horizon, from quantum fluctuations in the vacuum. One particle escapes, the other falls inward. Energy leaves. Over time, the black hole shrinks. And so, a new property of black holes was added: temperature. The surface gravity of a black hole defines how much energy it takes to escape, and that gradient gives rise to heat. It's not heat in the ordinary sense, but in the mathematical sense, it obeys all the rules: entropy, temperature, emission, evaporation. And yet, again, the paradox emerges. If information falls into a black hole and is later radiated out, where is that information stored? If it disappears, the principle of unitarity in quantum mechanics is violated. If it escapes, how? The radiation is thermal. It appears random. But quantum mechanics forbids true randomness in this context. Only apparent randomness, masking an underlying structure. This has come to be known simply as the black hole information paradox. Do black holes destroy information, or do they somehow preserve it? Over decades, this question has grown into one of the most serious puzzles in physics. Entire frameworks have been built to explore it. Page curves, replica wormholes, complementarity, firewalls, islands. Each proposal reshapes our understanding of what a black hole is, not just geometrically, but philosophically. Does the event horizon behave like a surface? Does it store data? Is the singularity real, or does quantum gravity erase it? The island paradigm, developed in recent years, proposes that information from within a black hole is somehow encoded in regions outside the event horizon. That quantum entanglement stretches in such a way that the interior of the black hole is represented holographically in the radiation itself. The information then is not lost. It is scrambled but present. In principle, if not in practice, recoverable. This strange counterintuitive idea might resolve the paradox, but it also demands that space-time be viewed as emergent, not fundamental, but arising from entanglement. And so, we return to that deepening suspicion. That space is not the arena of physics, but one of its consequences. That distance is secondary to information. That the shape of reality flows not from points and lines, but from the relationships between quantum states. Black holes are where these concepts become necessary. They are not just regions of high gravity. They are laboratories for the most extreme physics the universe allows. They teach us that geometry is not sacred, that causality even may be contingent, that the very structure of the universe is not a fixed stage, but a mutable fabric. One question remains: how do we test this? So much of what we've discussed unfolds at scales or energies far beyond current technology. We cannot probe the interior of an event horizon. We cannot rewind the evaporation of a black hole to read what was lost. And yet, we do have tools. Gravitational wave detectors like LIGO, Virgo, and KAGRA have opened a new window, one that listens instead of sees. These instruments capture ripples in space-time from merging black holes. From the waveforms, we can test the predictions of general relativity with astonishing precision. We listen to the final spirals, the coalescence, the ring down. In those waves may lie subtle hints, echoes, deviations, missing harmonics that could point to new physics, exotic compact objects, quantum modifications of the horizon, echoes of the interior. Each new detection is a data point in a growing map, and in the center of that map, the black hole. We also look at the shadows, the silhouettes cast against glowing matter. The Event Horizon Telescope continues to refine its images, capturing not the hole itself, but the lensed ring of light from the orbiting material. From these images, we can test the no-hair theorem. We can measure spin. We can watch the magnetic fields writhe and twist. And in time, we may find discrepancies. Signs that general relativity, while nearly perfect, is not the final story. On the theoretical side, physicists are working toward a theory of quantum gravity. String theory is one path, describing particles not as points, but as vibrating strings in multiple dimensions. Loop quantum gravity is another, describing spacetime itself as a network of discrete loops, a granular geometry at the smallest scale. Both theories aim to explain black holes from the inside out. They propose that the singularity is not a place of infinite density, but a place where spacetime becomes discrete, where the continuum dissolves. If so, the end of a black hole is not a tear in space, but a transformation, a place where the geometry we know gives way to something deeper. Perhaps that's what black holes have always been. Not ends, not anomalies, but reminders. Reminders that the universe is more than we see, that its rules are deep, strange, and, above all, unfinished. Reminders that knowledge itself has an event horizon, and that just beyond it, new physics waits, like the edge of a map, like a horizon line drawn in silence. We approach that horizon not with certainty, but with questions. We approach that horizon with questions, and that is perhaps the most honest way to meet the universe. By now, the story has curved and spiraled, like the gravity wells we've described, falling inward through layers of theory, history, mystery. It began with stars and ended with paradox, with silence. But there is one final layer to unfold, one last orbit to trace. It has to do with time. Black holes distort time, not metaphorically, but physically. The closer you get to the event horizon, the more slowly time passes from the perspective of someone farther away. This isn't a quirk. It's a consequence of how gravity works in curved space-time. To an outside observer, a falling object never quite crosses the event horizon. It appears to slow down, redshift, and freeze in place. But for the object itself, time continues normally. It crosses the threshold, it continues inward. It experiences a future the outside can never witness. This leads to a strange question. Whose time is real? Both, perhaps. Or neither in the way we usually think. In the vicinity of a black hole, time is no longer a universal rhythm. It fragments. It becomes local, personal, subject to frame and position. This relativity is not just physical, it is philosophical. A black hole divides reality, not only in space, but in experience. What is seen, what is felt, what is remembered. This leads us inevitably to consider what a black hole is to the universe itself. Is it a structure, an object, a process? Or is it, as some physicists now speculate, a kind of quantum computer? The mathematics of black holes reveals behavior that mirrors information processing systems. The growth of entropy, the scrambling of inputs, the transformation of data into unreadable output. Some suggest that the event horizon functions like a processing surface, a place where incoming information is encoded, distributed, and eventually re-emitted through Hawking radiation. Not destroyed, not lost, but transformed. The black hole, then, is not a destroyer, but a transcriber. It alters information into forms unrecognizable to us, spreads it across its surface, allows it to escape over eons. It is not a grave, but a translator, working in a syntax of gravity and light. Others go farther still. There are proposals now, mathematical, speculative, that the universe itself may be a vast, emergent computation, that space-time, matter, and energy all arise from information, that what we experience as reality is a pattern of interactions between fundamental bits. If so, then black holes are not the limits of this system. They are its defining features. They are the maximal expressions of what this computational universe can do: compress, transform, encode, and eventually release. Not every physicist agrees. Many are cautious. The metaphors are tempting, but the tests are difficult. But this is the nature of working at the edge. The closer you come to the horizon, the less certain your footing becomes. And still we try. There is a future in which we understand black holes fully, not just their properties, but their principles, not just their behaviors, but their implications. In that future, perhaps we'll use black holes as engines, tapping into their rotation, their temperature, their gravitational energy. Perhaps we'll observe their evaporation directly. Perhaps we'll even learn to read the Hawking radiation, to decrypt the information of stars long gone, civilizations long dead, matter long absorbed. Or perhaps not. Perhaps black holes will remain what they have always been: boundaries, markers of what can be known and what cannot. But even if they are never fully solved, their presence will continue to guide us. Because black holes do something rare. They force us to hold two truths at once. They are simple and complex, predictable and mysterious, perfect and paradoxical. They remind us that our models of reality are only that: models, maps of a terrain we do not fully understand. And like all good maps, they point not only to places we know, but to places we cannot yet reach. Black holes are not exceptions to nature. They are the purest expression of it. In the end, we look at them not because they are strange, but because they are honest. Because they reveal the structure of things. They do not deceive. They do not change with opinion. They do not yield to metaphor. They simply are. They curve space. They trap light. They obey the rules of entropy. And they persist. Across time, across scale, across the collapsing histories of stars, black holes remain, present, patient, complete. We peer toward them, instruments humming, equations unfurling, questions multiplying. And the answers, when they come, will not close the book. They will open it. Because at the center of every black hole is not just gravity, not just curvature, not just a singularity. There is also a mystery. And a mystery is not something to solve. It is something to live with. It is the open sky above a quiet earth. It is the memory of a photon that never returned. It is the final heat of a long-forgotten collapse. It is the shape of silence when it bends, and we, drifting far from that horizon, still feel its pull.